Square parallel plate capacitor. Two square conducting plates with sides of length capital L are separated by a distance capital D. A dielectric slab with constant kappa with dimensions L times D is inserted a distance x into the space between the plates as shown in figure. So here is our dielectric slab inserted a distance x in between the plates. Part A, find the capacitance of this system. Part B, suppose that the capacitor is connected to a battery that maintains a constant potential difference V between its plates. If the dielectric slab is inserted an additional distance dx into the space between the plates, show that the change in stored energy is du equals plus kappa minus 1 epsilon 0 v square L over 2d dx. Okay, so we have a capacitor, an air capacitor here, which has a distance L minus x on one side and L on the other side for its plates. And then we have this additional capacitor that is in between the same voltage terminals. And this has dimensions x and capital L. And the dielectric is thickness is capital D. So we have basically two capacitors C0 and Cx that are subject to the same potential difference. So the same potential difference. Therefore, what can we say about these two capacitors? They are connected in parallel. So C0 and Cx in parallel. Now, what is the capacitance of the air capacitor C0? It is epsilon 0, the area of its plates, L times L minus x over the separation between the plates. So once again, we have this side L minus x, this side L. So if I write here, this is capital L minus x, and this part is capital L, because these are square, remember. So that's the dimensions of the plates. And as for the capacitor Cx, we have a dielectric constant kappa, so it's kappa times epsilon 0. And what are the dimensions here? It is x and L, so the area is L times x, and the separation between the plates is capital D. So what is the equivalent capacitance for this configuration? Two capacitors connected in parallel, the capacitances will add up. So we will have C0 plus Cx. It is in epsilon 0 L over D parentheses, epsilon 0 capital L over D. I have capital L minus x plus kappa x. So I can rewrite this result as C equivalent is equal to epsilon 0 capital L over capital D. Then I have L plus kappa minus 1 x. So that's the equivalent capacitance of this configuration. Now let's move on to part B. Well, what is the stored energy as a function of x? It is basically 1 over 2 C equivalent V squared, or Q squared over 2C equivalent. So if I substitute here the C equivalent that I have calculated, epsilon 0 capital L over D, but this is 1 over 2, so it's going to be over 2D capital L plus kappa minus 1x v squared. So if I inserted an additional distance, then the change in the stored energy du will be the differential version of this. So this is going to be, since there is no x here, the derivative is 0, so only this term gives me a contribution. So du will be plus epsilon 0 capital L kappa minus 1 v squared dx divided by 2d. So I'm considering incremental changes in potential energy due to incremental changes in x. There is no x here, so that has 0 contribution. This becomes epsilon capital 0 capital L kappa minus 1 dx v squared over 2d. Let's check if this is the suggested answer. It is equal to this, so therefore I see that this answer that I have obtained here is correct. Okay, so in this problem I'm considering a square parallel plate capacitor. A dielectric is inserted at distance x into the space between them. Now I form two capacitors, an air capacitor with dimensions L minus X, L and D, and a capacitor which has a dielectric slab inside with dimensions X, L and D. The corresponding capacitances are C0 is epsilon 0 A over D, area is L times L minus X, and Cx is kappa epsilon 0 because I have a dielectric constant kappa other than 1. Area is L times X divided by D. And since they share the same potential difference, they're connected in parallel, the capacitances add up to give me the equivalent capacitance. The stored energy is given as 1/2 C equivalent V squared when there is a potential difference V applied between the two terminals. And if I write this potential energy, a small change in X will only affect this term here, so this term goes away, and I see that the change in stored potential energy becomes plus epsilon 0 L kappa minus 1 V squared over 2D dx.